familiar that we have studied this chapter, and we are just studying the occurrence of metals. So what actually we does in the occurrence of metal? We have different types of ore, like we have sulfide ores, we have carbonate ores, we have oxide ores, and we have halide ores. Okay. After removing the gangue, or by enrichment of ore, after removing the impurities, sand particle from this sulfide, carbonate, oxides, and halide ores, we have enriched the ores. Means it is not having dust particle now. Now, what in the next step? What we does? We do for sulfide, and we do in the presence of oxygen. We heat the sulfide ore, and that is called roasting, and it get converted into its oxide form. Similarly, for carbonate ore, in the absence of air, we heat it and we got it calcination, heating, here also heating. Then these carbonates ores are converting into their oxide form. They are already in oxide form, and in halide, we will not don't convert it into oxide form. Don't convert into oxide form. Okay, so these carbonate and sulfides ore were converted into their oxide form. For example, if we are having ZNS, then on passing oxygen or in heating with oxygen, they will get converted into ZNO plus sulfur dioxide. If we are having calcium carbonate on passing, calcium carbonate on heating it in the absence of air, it was get converted into calcium oxide plus sulfur dioxide, carbon dioxide. And these were converted into carbon dioxide or calcium oxide and zinc oxide. And why we are converting? Because if we are going to extract metal, so metal can be extracted from the oxide form easily. Metals can be extracted from their oxide form, rather than more easily. Okay. And in this form, if we are just going to extract metal from zinc sulfide and carbonate, it is means it will take extra process. Okay, so it will harder. So that's why we convert sulfide ore and carbonate ore into their oxide forms. And oxides ore are all also in their already oxide in their oxide forms. Okay, you understood? Understood, everybody?
Sir, ZNO and CO can be converted into
later they will be converted into metals. So talking about these, there are different types of ores. Let's talk about this. That we have sodium, potassium, calcium, magnesium, aluminium, zinc, iron, tin. I have just modified this one. Sodium, calcium, potassium, sodium, calcium, magnesium, aluminium. Then modified chromium and manganese here. And then carbon. Then zinc, iron, tin, lead. And then hydrogen, then copper, then mercury, then silver, then gold. Silver, gold, platinum. Ag, Au, Pt. Okay. Understood? Now, if we are talking about this one, that these ores, these exist in the native state. These ores, for example, the ores of these Cu is Cu2s, Hg is Hgs, Ag is Ag2s. These ores can be converted into the metals by simple roasting. by simple roasting. Simple roasting is if you roast it, you can simply get the metals. For example, if you have HGS, if you heat it in the presence of air, you will get first HGO, then SO2, and then HGO. When heated, again it continuous heating, it will get converted into Hg plus O2. Similarly, Ag2S, when heated in the presence of oxygen, it will gives you Ag O plus SO2. But if we have AgO further, we are Ag2O. Further we are heating, it will gives you Ag plus O2. But in case of copper, it is a means it is less reactive, sorry, more reactive than this one. So it require a reagent. But here reagent itself behave a crushed ore itself behave as a reducing agent. For example, if you are having Cu2S, when it is heated, it will give you Cu2O plus SO2. But here Cu2O can't be, by simple heating, it can't be converted into Cu plus SO2. It can't be converted like this. It need a reducing agent. So here the reducing agent is itself crushed ore. This crushed ore, Cu2S. When you heat it, then it will give you Cu plus SO2. So here crushed ore itself behave as reducing agent.
Okay, I found this on the web form as reducing agent.
Are you understood?
Yes, sir.
Yes, sir.
Okay. Everybody in the class understood? Please, if you have not noted this one, please note it down.
Yes, sir. Done.
Done?
Can
Noted?
you show
Hmm?
Cu2S?
Cu2S is Cu2S. What are you asking about Cu2S?
The simple roasting, like converting into
Yes.
metal.
Yeah. They can be converted by heating, simple roasting. Okay. But these metals required some reducing agent, and that is carbon. If you heat it, for example, if I'm talking about ZNS, okay, plus carbon. So they ZNS first get converted on roasting, it will give you ZNO plus SO2. But if you continuously heat it, ZNO, and even if you use it with ZNS, it will not give you ZNO. No, it will not give you. It need a reducing agent, powerful reducing agent. So that is carbon. When you use it carbon, you will get ZNO will get converted into Zn plus U. So that is called, these metals that are here, Zn, Fe, and if they are in their oxide form like ZNO, like Fe2O3, because by roasting and calcination, we have converted them from zinc sulfide to zinc oxide, okay, into their oxide forms, okay, like PbO. So if they are having their oxide form, they can be reduced by carbon. Reduction with carbon. Reduction with carbon. These are the mid-reactive metals, okay? And these metals can be reduced by aluminium. For example, if we are having manganese oxide, MnO2, so these metals, you can check it. I have written here that these metals are written above above carbon. So these here carbon cannot be used as a reducing agent. For example, if you are having MnO2 and you are reducing with carbon, so it will not gives you Mn plus CO2. No, it will not gives you Mn plus CO2. Because carbon is not as much as means it cannot oxidize here. So it cannot reduce here. So carbon, instead of carbon, we have aluminium here. So when the mixture of this one and this one is burning red, magnesium ribbon is added to this one, the reaction will start and will gives you Al2O3 plus Mn in liquid state. Similarly, if you have Cr2O3 and we have aluminium, then it will gives you Al2O3 and chromium in the liquid state. This reaction is so exothermic that the heat liberated out in this reaction will gives you metals in the molten form. And because of this advantage, we use sometimes Fe2O3, which is a mid-reactive metals, which can also be reduced with carbon, but we use aluminium for this one. Okay, to give Al2O3 plus Fe in the liquid state. Okay. Okay, so this molten iron, we use this reaction for joining the railway tracks. Okay, here we use this one, and this is the molten iron will comes here and will filled here. Okay, in joining the railway tracks. So this reaction is special, and this reaction is named as thermite reaction. Got it? Thermite reaction. Thermite reaction. So these metals that we are talking about, like chromium and manganese, they can be reduced by aluminium and iron, which can also be reduced with carbon. But we, in order to get it in the melted form, we sometimes use aluminium also for its reduction to get iron. Okay, and these metals are highly reactive metals, and for these metals we used electrolytic reduction. Electrolytic reduction. So again, these metals by simple roasting, by heating, these metals by reduction with carbon, these by aluminium, and these by electrolytic reduction. Okay, by aluminium, Okay, you understood? So if we are having NaCl, for example, NaCl in molten state, so we just take the NaCl in molten state, and then we pass the electricity to it, high voltage electricity, and it will gives you Na plus chlorine gas. Okay, you understood? This is electrolytic reduction. This I have explained you, and you have also written in your copy in the previous class. So let's move further. Now, by various methods, we have converted the metals into their from by simple roasting and calcination. We have first converted the metals from the ores from sulfide ore or carbonate ore into their oxide forms, and later by using simple roasting, by reduction with carbon, by aluminium, by electrolytic reductions, depending on the type of ore or the oxide, whether it is reactive metal oxide, whether it is a least reactive metal oxide. We use different methods to remove the oxygen from the metal, and we get the pure metal. Okay. Okay.
Yes,
Now,
sir.
is still the metal that we are having here, it does not have, it is not pure at highest purity. You cannot say it must have purity. Does not mean it is going to have impurities like sand. No, purity means that it must have 100% same atoms, same kinds of atoms. Means if I'm saying that if copper is having the atoms of copper, but sometimes gold, then copper, then silver, then copper. So you know that copper, gold, and silver are precious metal, but still this strip is not going to have all atoms of copper, so we'll consider it as impure. Got it? So it is not pure, so we have to replace this one and we have to bring only copper atoms. So this is called purity. Okay, So for this, we use electrolytic refining. But we use electrolytic refining. You understood, dear students? And what happens in the electrolytic refining? Let me explain you. First, we take the electrolytic cell. Okay. And then when we make a thin metals rod, which is of the metal which is pure and which is of same metal that we are purifying. For example, if we are purifying the copper, so we take a rod of pure copper metal rod, okay, and the impure rod is taken like this. The impure rod is taken like this. Okay. Madhya, why are you late? Okay. So what we are doing here, we are doing electrolytic refining. So for example, if we are just purifying copper, then we are just going to have a thin pure copper, thin pure copper metal rod, and the thick impure metal rod here. You understood, dear students? You understood? You understood?
Yes.
And the impure one is connected with anode and the pure one is connected with cathode. So many times the question is being asked that during electrolytic refining, which metal rod is made as anode, impure or pure? Sometimes it is anode is made impure rod or pure rod. So you have to keep in mind that pure metal is made as of a cathode is made cathode, and impure the rod which you need to purify, we need to make it pure. Sorry, at anode. We need to connect it with positively charged. Okay, you understood?
Yes, sir.
Okay. Okay. Now, what is going to happen here? Let me explain you. We add the same electrolyte. If we are just if we are just purifying the copper, then we will have copper sulfate as the electrolyte. So if we are just purifying copper, so we will have copper sulfate, Cu2 positive and SO4 minus 2. Because it is electrolyte, so it will be dissociated in the ions. So I'm just writing here. Okay, Cu2 positive, SO4 2 minus. So like we have, okay, got it? Yes, students.
Yes, sir.
So let me first you explain me that during electrolytic refining, what we are doing right now. The impure metal, that if we are, suppose if we are just purifying the copper metal, then we will take a thin pure metal rod and we will connect it with negatively charged terminals or cathode. And this will be connected with the positively charged material, that will be anode. Okay. Okay.
Okay,
And this is
sir.
it is going to have copper atoms, but sometimes it is also having gold, like gold, silver, platinum. Okay. So this is going to have some impurities here. Now what happened? When you pass high voltage current to it, then what would happen? This Cu2 positive ions will move towards this cathode. So at cathode, what is going to happen? Look at this, everybody, please concentrate here. When we pass electricity, then this Cu2 positive ion from the sulfate ion, from the electrolyte, will get 2 electrons and will form copper solid. Copper solid is brown in color and this copper Cu2 positive ion is blue in color. So what is going to happen? This brown color copper from copper sulfate solution will start depositing over this rod. Okay. Got it? Got it? It will start depositing here. And what would happen? if all the Cu2 positive ion will goes to this one, then the concentration of SO4 minus 2 ion will increase in the solution. We have initially same amount of Cu2 positive ion and same amount of SO4 minus 2 ion. But if Cu2 positive ion, only Cu2 positive ion start moving to this rod and get stucking over here, converting into copper atoms. So you will find that after some time, the concentration of these ions will increase and this will decrease. Why are not everyone replying?
Yes, sir.
Let me check who is not answering. Ashwin, Amar, got it?
Yes, sir.
Vidwan, Madiha,
Yes, sir. Yeah.
are you there, Madiha?
Yes, sir.
Why you joined late?
Sir, I was outside.
So if we have this copper, now what if the SO4 concentration will increase, then what would happen? The same amount of, in order to make the electrical neutrality, means if the more SO4 ion will be there in the solution, then what would happen? The electrolyte will become negatively charged and it is not possible. So to balance it, the equal amount of this copper ions, copper atom will get converted into copper ions. So what would happen at anode? What would happen at anode? At anode, the copper atom that is present here. Why not the Au atom is losing the electron, silver atom is losing the electrons? Because you know that those metals that are like we have copper, then we have mercury, then we have silver, then we have gold, platinum. So if we having metal that are below copper, they will lose electrons at lesser rate as comparison to this one. Because this is the reactivity series and this is made on the basis that which elements will lose electron first will be considered as at the top. So this is the at highest purity, it can lose electron very easily, then sodium, then calcium, then magnesium, then aluminium, then zinc, then iron. So here copper, if copper, mercury, silver has to lose the electron, which will lose electron first? Copper. So here what would happen? The copper atom will lose electron. Copper solid will lose electrons and will get converted into copper 2 positive ion. So this equal amount of copper, this copper, which is brown in color, copper atom will get converted into copper ions. So one by one atoms from this rod, copper atom from this impure rod will come into the solution, and from the solution it will goes and will again form copper atoms and will deposit it here. Okay, on this one. After some time,
So
what about sulfate ion?
AU and AG.
Au and Ag will not lose electrons. After some times, you will find that each and every copper atom will move toward this, first into this electrolyte, and then from electrolyte it will move into this one. You will find that after some times, this rod will become thicker and thicker. This rod will become thicker and thicker. Okay. And this rod will disintegrate. This rod will become thinner and finally will disappear. And the impurities in the form of gold, platinum will remain at the bottom. Okay, so this is anode mud. This is called anode mud. Okay, so if someone asks you that write a note on electrolytic refining of copper, so what we does that electrolytic refining is the method for obtaining the purest form of metal. Okay, and in this what we does, we take we take a thin pure copper metal rod and we make it cathode, and the impure metal rod is made anode, and the same metals solution is taken or salt is taken as electrolyte. So in case of copper, we will take copper sulfate as electrolyte, and dilute H2SO4 is also added to increase the conductivity, so that more conduction can easily take place. Okay, and then what is going to happen? On passing current, the Cu2 positive ion will reduce, means will reduce to copper atom. This is reduction. Cu2 positive is getting converted into 0. So plus 2 is 0, it will reduction. Addition of electron is reduction. So and always at cathode reduction take place. So Cu2 positive ion from electrolyte will get converted into Cu solid, will get deposited over the cathode. And in order to maintain or maintain the electrical neutrality, the same amount of copper atoms are oxidized, means they will at anode oxidation take place. Okay, removal of electron is oxidation, and here reduction is taking place. So the same amount of copper atoms get converted into copper ions, Cu2 positive ion. So slowly, one by one, copper atoms will comes into the elect and will form copper ion, and then from copper ion it will get again converted into copper atoms. Okay, and this process continue. At the end, we will find that the cathode become thicker and thicker, and the anode will disintegrate, leaving impurities as anode mud. Okay. Okay.
Yes, sir.
So please first draw this one. Draw this
So
one.
the anode will get oxidized, means
Yes,
oxidation.
yes, at anode oxidation take place. Addition of removal of electron is oxidation.
Oh, okay, sir.
So what is that anode mud?
Anode was the impurity that it may be contain the particles of containing the particles of silver, gold, platinum. That was here. Okay, that was this one going to lose the electron, so they will settle at the bottom. Okay, after the reactions take place.
Done, sir.
Done, sir.
Okay. Okay. Everyone done? So please write the statement of this one. Write a note on electrolytic refining on copper. Note it. If you are getting any problem in understanding any word, please let me know. Okay.
Okay, sir.
Sir, is the process of obtain?
It is a process of obtaining pure metal to highest purity.
Uh,
Obtaining. This is obtaining. Done.
No, sir.
Done,
Noted.
sir. Done, sir.
Done, everyone?
No, sir.
Noted fast. Done?
Done, sir.
Done, sir. Done.
Note this one also, and then note this table. This table is important. Sometimes the question may be asked that the name the ore for bauxite is an ore for. So you must remember that bauxite is an ore for aluminium metal. Okay. So this may be asked bauxite, copper pyrite. So important. Write only this one. This one bauxite, copper iron pyrite, zinc blend, then magnesite, on silver, pyrite, hematite, rock salt, cinnabar, magnetite, glens, limestone. Write these only. How many I have left? 1, 2, 3, 4, 4 I have left. Okay. Not it. Write the whole. Okay. Okay. Write the remark. Sometime it may be asked along with the formula.
So what you wrote after disintegrated?
Disintegrate, leaving behind the impurities called anode mud.
Okay, sir.
Done.
No, sir.
Noted. Done. Noted.
Yes, sir.
No, sir, no.
Noted fast.
Done, sir. Gone.
Done, everyone. Okay.
Done, sir.
So now we are going to have. Okay, tell me which one is the correct option for this one? Which one is the correct option for this one?
Sir, C option. C.
Yes, C is correct. From anode, Cu atoms is coming and forming Cu, and this Cu2 positive is going to this one, and this is positive, negatively charged cathode. This is this one. Okay. This and this is same, but you see that here positively charged is written as cathode, while positively charged is anode. So this one is incorrect. Okay. So anode mode is in between the anode, so this is correct. Okay, dear students, so this one C is the correct. Okay, so let's last topic that is of this chapter, that is alloys. What are alloys? Alloys are the homogeneous mixtures of two or more metals or metals and non-metals. Okay, alloys are the homogeneous mixtures, homogeneous mixture mixtures of two or more metals, metals and non-metals. Okay, understood. For example, bronze, example of metals and non-metals and metals. Like we have bronze. Okay. Similarly, we have bronze first. We have brass. Okay, this is copper and tin. This is copper and zinc. Okay, and metals and non-metals like steel. Steel, we have iron plus carbon. Okay, so this is metal, this is non-metal. So this is an example of. Okay, and why alloys are made? Alloys are made in order to attain the stability or durability, to increase melting and boiling point, increase or decrease melting and boiling point, making the metals lighter. Okay, for example, if we need some metal or something metal which is going to have lighter in weight, but it is more durable. Okay, it has high tensile strength. So we cannot use only aluminum to make a spacecraft or aircraft. Okay, so we used alloys which is lighter in weight of aluminum, and like magnesium. Magnesium means aluminum mixed with magnesium. So when you mix with aluminum with magnesium, it will give you magnesium, and it will give you an alloy. Magnesium is an alloy which is lighter in weight, lighter, durable, and used for making aircraft. Okay, similarly, stainless steel and steel only. Iron, initially used. Here we have iron. These atoms are joined like this. So initially, if we have iron only, there are distortions take place in this iron. The one layer of atoms slide over the other, like it goes into the space here, and one layer slide. So this result in distortion in in iron. So what we does, we just mixed the copper, melted and mixed the copper atoms. Copper atoms are small, carbon atoms. They are small and they come into the intermolecular space of this one. And they form what they form? They form steel. This is carbon atoms. So now the distortion does not happen, and no, or we can say the layer will not slide over one another like here. If we are having this Fe, so the iron atoms will slides over one another. But here, if we place carbon atoms in the voids in the intermolecular in the atomic interstitial space, then they will not slide, and this will gives you steel only. Steel, and this steel is used for making railway tracks. Okay, railway tracks are made up of steel, in which iron is mixed. Okay, 1% carbon is mixed. 1% carbon is mixed. Okay, dear students, you understood? In order to prevent
Yes,
it
sir.
for distortions. Now the heavy rails or train can pass over it on the railway track. But if we have only iron, then distortion may take place. The railway track may bend. Okay, bend due to heavy load. It's because distortion is possible. But here, when we mix carbon, 1% carbon atom is smaller in size as compared to iron atom, so it goes into the voids. And similarly, to decrease the melting point, to increase the melting points, we use this one. For example, if we have two elements like AA, and another one we have BB, another one we have BB. Okay, and they don't like each other. For example, A atom don't like B atoms. They hate each other. So they will repel each other. Okay, but they have a strong force of attraction between BB, intermolecular attraction or interatomic attraction. And similarly, this one is also, they are also having intermolecular attractions. So when we mix them, we will have A, then B, then A, then B, then A, then B. And because of that A and B, they will repel each other. They will repel because they don't like each other. So if there is a force of attraction X here between A atoms and B here, Y here between these atoms. So here the force of attraction will be lesser than X plus Y. force of attraction will be less than x plus y. So here we will simply say that this A and B alloy will have low melting point. Will have low melting point. Melting points. So like examples, we have tin and lead Pb lead. They forms an alloy called solder, and this has low melting point, and it is used for soldering wire. Used for soldering wires, chips in electronic devices, okay. And similarly, if we need an element which is more durable and will have more melting points, so we will find those elements that is going to have, means AA and BB will like each other more than AA, and means there is a force of attraction, more force of attraction between AA and BB, AB particles than AA and BB. So when we have some elements like AA, they are attracting each other, and BB, they are also attracting each other. But when A and B are mixed together, they have greater force of attraction. A and B, when mixed together, they have greater force of attraction. So in that case, they will attract each other, and with the melting point will increase, and durability will also increase. Okay, the metals will not distort and will have high melting points. So depending on the type of need that we need, we make alloys. So alloys, the purpose of making alloys is to increase or decrease the durability, to increase or decrease the melting point, to increase the tensile strength, okay, to prevent it from rusting. For example, in stainless steel, we use chromium, nickel, carbon, iron. So it is used for preventing from rust. Okay, you understood? Everybody understood?
Yes, sir.
Okay.
Yes, sir.
So this is the uses of alloys. Okay, the alloys are being used for making this one. And here it is that ferrous alloy, the types of alloys, there are ferrous alloys. Ferrous alloys are the alloys in which one of the constituent is iron. One of the constituent is iron. Means if an alloy consists of iron, for example, steel, and stainless steel both, steel. So if it is iron containing alloy, that is ferrous alloy. Similarly, amalgam is also an alloy in which one of the constituent is mercury. One of the constituent is mercury. Okay, dear students, you are getting mercury. So if we have any alloy like sodium amalgam, then it means that sodium plus Hg mercury, when they mix together, they form sodium amalgam. Okay. Okay, dear students.
Yes.
Okay.
Yes, sir.
So just wait a minute. This is the last thing that I'm going to. Here we have a table. Okay. And write the alloys, write the names of the alloy and their constituents only for brass, bronze, duralumin, magnesium, solder, stainless steel. Okay, write that brass is made up of copper and tin. This is made up of, okay, and this one is made up of, and their uses. Just write this one, okay? And then if you're done, then you can leave the meeting, okay?
Okay, sir.
We have finished this chapter. In the next class, dear students, I'm going to tell you that every student has to join the class, because in the next class we're going to start the carbons compound chapter, and in carbons compound chapter is very important chapter for the organic chemistry. So your base must be very strong for organic chemistry. So no one is going to leave any class of carbons compound, because it's very important class. Okay. Okay, so please note it down, and if you're done, then you can leave.
So we have to write that uses also. So should we write uses?
Yes, uses you have to write. Only for those that I have ticked. Okay.
Okay, sir.
Sir. Thank you, sir.
Thank you, sir.
Done. Thank you, sir.